see what we can do here. Okay, we're going to talk about limits, and I want to first of all let's get some kind of an informal definition of that. Okay, what is a limit? Do you know anything about limits already? You heard the word. You dealt with it a little bit in pre-calc, right? Yeah. Furthest point you can go to, okay, that's a way to get us started thinking about it a little bit. What does the word limit mean in just everyday lingo? And that's one example. The furthest point you can go to. You want to work to your limit. Restriction. Okay, a restriction could be a restriction. Like parameters, kind of. Okay, by restriction, some places the limit would be that you can go up to, but not actually ever get to that point. You can reach for your limit, but you may or may not be able to reach that. What we'll find out throughout the year more and more is that regular, everyday talk can sort of, reach for, but never quite handle mathematical concepts well, especially more advanced mathematical concepts. We've got to develop a distinct, precise language for math that is unambiguous. And limit is a good example of one of these concepts where we can sort of talk about it a little bit, but one of the beauties of language, and what makes books fun to read is that language is colorful and it's subjective to some degree. When you read something, you get to kind of bring your own little interpretation into it. But in math, we don't enjoy that luxury. Math is completely different. Math is something that needs to be precise because when we talk about a concept and we build on that concept, we all have to have a very accurate idea of what the heck we're talking about, right? And so with limits, this is something, it's a seemingly, you look back on it and say, wow, that's not that big a deal. But we got to build this in a rigorous way so we all understand this exactly the same way, and we use a language, and we construct it in a way that allows us to build on it for months and months to come, because most of what we do in calculus at some level actually depends on this relatively simple concept of a limit. Okay, so what is a limit? Now, if we take a function, I'm just going to pick just some random function, like so. Imagine this. Now I'm going to introduce a new species of critter here called a calculus ant. The calculus ant is two-dimensional, and it's infinitely small. Okay, so how can you see it, right? But it walks along these functions. The calculus ant will develop some abilities, some extrasensory abilities here that throughout the year that we'll utilize. But for now, the calculus ant has this ability. It can always sense where it is on the XY plane. Okay, so it's walking along this curve, and it knows as it goes. It's like a built-in compass of sorts, or GPS. It knows exactly where it is. Now, what if a two-dimensional thick calculus fog rolls in here? So the ant is walking along the function, and it can't actually see where it's going, but it still senses it, right? Would you agree that if I put a little red dot right here, as the calculus ant, walks along, we'll make him orange, as he walks along this function like so, taking these little itsy-bitsy steps, infinitesimally small steps in fact, as he gets right up close to that thing, he knows where he's going to land, doesn't he? If there's no fog, he can see it, but what if a fog rolls in? If a fog rolls in so he can't actually see where he's going, he's still going to sense being at that red dot, right? That's the limit. That's the limit. It's not because that's where he actually goes that that's the limit, but because it's where he anticipates he's going to go when that fog rolls in. You see the difference there? There's a key difference. Let me just hang on. Eric, go ahead. Hey. At all? I can't right now. Maybe we better do something else today. Yeah, I'll look into it. I don't know what's going on. Sorry about that. Yeah, I don't know. Okay. Bye. Okay, so that was a bad place to break my train of thought. So anyway, that's the key difference. The difference, and we'll make this more vivid in just a second, but the fact that the ant anticipates stepping there represents the limit. The fact that he actually steps there is actually irrelevant. Okay? Now, what if a fog rolls in so he can't see where he's going? Wouldn't you agree that that's still the limit? That's still where he thinks he's going to step as he walks along this curve from the left or from the right, for that matter. It shouldn't make any difference. As he walks from the right, maybe a different calculus and with the same abilities. They both blindly anticipate stepping on that red dot, right? So the red dot, therefore, is the limit right there. In fact, the limit is really the y value, but we'll get more to that in a second. Okay, so how do things change if I do something weird here? If I change this function a little bit, I'm going to move 1 point on this function. I'm going to erase, oops, that's too big. I'm going to erase this little guy right here, and I'm going to put a hole in the function. So that function doesn't exist at that 1 point, just one single point though. Okay? Does that change the limit? Does that change where the ant thinks he's going to step? No, it doesn't. So where's the limit? At that one non-point, really, at that one spot right there where there's a hole in the function. Because when the fog has rolled in, the ant can't see where he's going. He still blindly thinks he's stepping on that point that used to be red, right? Now, what happens when he actually gets there? As far as the limit is concerned, we don't care. It doesn't matter what actually happens at that point. The limit gets at the concept of what's the trend of the function as you approach that point from either side. Okay? I mean, this is very conceptual. We'll be more mathematical here in a little bit. But you get the idea? Here's another way of visualizing this. Let's say that for the rest of my life, I'm gonna take steps towards the door, and I'm going to cut my distance to the door in half with every step. And I guess I should preface this by saying that we're going to make the assumption that space is infinitely subdividable, which modern physics tells us recently that probably isn't the case. There's probably some lower limit called Planck limit that you can't go below if space doesn't mean anything. But we'll just ignore that. We'll be in a mathematically perfect universe here for a while. And so if I keep cutting my distance to the door in half with every step, first of all, will I ever hit the door? No, we all see that, right? I'll never get to the door. Is there any point, if I had an infinitesimally fine pointed pen, is there any point I could draw on the floor that I would never step on? That's a little tougher question. Now think about that one for a second. I'm cutting my distance to the door in half with every step. If I had an infinitely fine pointed pen, is there any point I could draw that's not on the door, that's actually on the floor, that I wouldn't step on? That's a tough one. I'm hearing some yeses in the notes. Oh, well, let's say that my foot is still pretty big. So when I step on or over a point. Okay. Could I either get to or go past every point that I draw?
Yes.
I'm kind of curious what people think about this. Think a little bit. Does anybody? How many people think? Just have a little. Don't be shy here. This is no big deal. Raise your hand if you think that there's no point I could draw that I wouldn't either step on or step past. Okay, a few brave souls. Raise your hand if you think I could draw a point that I could never step on. Okay, defend yourselves. Those who just raise your hand, tell me, how could I do that? How could I draw a point that I'll never step on? Assuming I live forever, too. This is a pretty good example.
Unless it's directly on the door, you're gonna keep having your distance between the door, and at some point you will eventually step over a point that you draw.
That's a good way to say it. Actually, that just settles the whole point right there. Yeah, it's true. There's no point I could draw. That's absolutely right. There's no point I could draw that I wouldn't step on, right? Because I get. Now here's an important word in math. This is a really good one. You sound smart when you say this too, but it really is a good word. Because I could get, we'd say in math, arbitrarily close to the door. Meaning there's no limit to how close I could get to the door. If I walk long enough, I continue to get closer. We run time forward infinitely. Therefore, there is no point that I could ever draw that I wouldn't step on. Because if I just wait long enough, I'll get there, right? You might say though, What about the point next to the door? Is there such a thing? There's really not, is there? Because if I keep focusing in closer and closer, any point that I draw that I think is next to the door, if I focus in more closely, well, in fact, how many points are between that point and the door? An infinite number. Because I can keep on increasing my field of focus, and as you get closer and closer, things get spread apart more, right? Does that make sense?
Yeah.
Okay, to me, that's actually a very good representation of what a limit means, because what is, after all, the limit of my motion? The door. Yeah, the door is the only point that I'll never actually step on, but it's the one point that I'm always approaching. Does that make sense? Okay, so that's really kind of what a limit is. So, so this still is the limit right here, isn't it? Okay, now what about this? I'm going to change some things up here. What if I do something like, I'm going to get really weird, and I'm going to take that one point, instead of just erasing it, I'm going to put it down there. So in reality, as the ant walks along this curve, he's taking these little bitty calculus ant steps. He walks along, he thinks he's going to step there, but when he actually steps on that point, he's just beamed down to that dot, right, for that one little infinitesimally small step. Next step, he jumps back up onto the curve and he's on his way. And we could reverse that story if we just walk backwards in the other direction. Okay? So now where's the limit? Which dot? Top dot or bottom dot? Which one's the limit?
Because that's where he leads to start.
Let's take another poll here. I'm just kind of curious. Raise your hand if you're voting for the top dot. Raise your hand if you're voting for the bottom dot. Don't people? Okay, why the bottom dot? Now I can see both sides of why people would say this. I really can. Yes, sir.
You said something about the limit being the y. So when it should be where the height is.
Okay, yeah, okay. Forget I said that for a second. Let's just think about it. We'll get to that a little more in a second. Sure.
At one point he steps and then isn't it on the blacktop and has to take another step to go back up on the line?
Right. And I can see why. Let me paraphrase. I think. Tell me if this is why you're saying this. Because earlier we said as we walk along, it's where he's actually the red dot. The location of the red dot was the limit because that's where he would have landed, right? Okay, but that was only because where he would have landed at that point coincided with where he thought he was going to land. Remember that the limit part is only concerned with where he anticipates going. It has nothing to do at all with where he actually ends up. Nothing to do. So it's the top dot. Yeah, question. Oh, it's the top dot because the ant, up until the very last final step, when I actually just get tired of this exercise and kick the door, or the ant just takes that last step, that's the only time that he actually ends up on that dot. When the calculus fog has rolled in, he has no idea the dot's there. The whole time he's approaching that point from either side, he thinks he's going to land there, right? So that's still the limit. How about that? Okay. All right. So let's take a look at a couple ways we could explore this. We already looked at one. When we talk about limits, there are really three approaches we take to finding limits, right? We just did the easiest. The easiest way is by looking at a graph and just seeing what's happening. We could see pretty clearly on this one by looking at that graph that that's where the ant thinks he's going, and therefore that's the limit. Okay? Another way we could do it is numerically. Oops. We'll explore that one here real briefly in just a second. And then the third way is something we're going to hold off on for today because it takes a little more thought and time. Is analytically, algebraically, in other words. There's a way that we can do this that's very mathematical and ironclad, and we can all agree precisely on what's going on. Wouldn't you agree that in a math class, looking at a graph is nice, but it's not very perfect, We don't, you know, I mean, we don't really, what if we focus in on this thing and we find out that we can't see it right now? Well, that's a bad way to say it. I'll just leave it at that. Analytically is the way that we can do this without having to go through the bother of drawing a graph or knowing what the graph looks like. What if the graph is very complicated? And numerically, you'll see in a second is, I mean, you can capture the trend, but once again, it's just not as absolute. Okay, numerically, what does that mean? What does numerically mean?
Using numbers.
Using numbers, yeah. We're going to analyze something by plugging in appropriate numbers and seeing what kind of results we get. We do that a lot in calculus. In fact, there are some techniques that we're going to do. I'll just set you up for this. There are some things in calculus. We'll spend a great deal of time learning how to do the tricks of calculus, which are amazing. You're going to absolutely love it. But once we learn these tricks, we'll find out that there are some odd cases where this beautiful thing, this beautiful calculus that we're looking at, doesn't work. It literally doesn't work. And so we have to use numerical analysis. We have to actually just make an estimate based on numbers that's not perfect, which is weird that we have to do that, but it'll happen from time to time in math. Okay, numerically. All right, let's look at, I just made a little spreadsheet here. In fact, I just made a little spreadsheet here. Are you guys good at using Excel? Because that's something you should do. In fact, I'm going to probably make you guys do some Excel stuff just so you get used to it. It's so useful. It's such an amazing tool. It looks like it's pretty boring, but you can do incredible stuff very, very quickly in Excel by just dragging formulas, and it's good stuff. I mean, everything from making a grade book to, I don't know, all kinds of awesome things. So here's what we're going to do with this. We've got this function up here, x cubed minus 1 divided by x minus 1. And we're going to take a look at what happens to the y values represented by the function as we change the x values. Now here's the little journey that we're going to take, and you can even visualize the ant doing this if you want to. The ant's going to start off at x equals 0 and take steps, in fact decreasingly small steps, if that makes sense. He starts off by taking a step of width 0.5 and then 0.4 and then 0.01 and then 0.001, etc. And he's approaching a value of 1. We're going to watch that journey, we'd say in calculus, from the left, from values of x smaller than 1 up to 1, and then we'll look at the journey from 2 back down to 1. We'd say in calculus from the right. Okay, now watch what happens to these y values as, whoops, that's what I want to do. Oh, they won't do that. It's stealing all my thunder. What do I do here? My goodness.
Control Z.
There we go. Oh, yeah. Okay. Let's see if I just start this down one at a time. There we go. How about that? So we can see, as expected here, maybe, the function is getting a little bigger. It's growing. Okay, good. Yeah, it's growing, right? Let's pause a second here and let's go down to the bottom and look at that and see what's happening there. Let's see, I want to maybe get rid of, man, I'm still not really used to this new Excel here. Can I drag those up a little bit? No, shoot, I can't I? Let's do this. There. Okay, let's start at the bottom. When x equals 2, y is already clear up to 7. So the ant that's on the right, he's going to walk backwards a little bit. See what happens to him. What's going to happen to the y values, you think? Going to decrease, sure. Yeah, look, they're getting smaller. Pen isn't very precise. Anyway. Oh, I'm going the wrong spot. No wonder. Let's go down here and see what's going on. Oh yeah, those are getting smaller. Let's go back up here. Those are getting bigger. What do you think? What value are they approaching? Kind of looks like it, doesn't it? Yeah. Now what's going to happen? Let's see what happens when we get there. Oh, it blew up.
Oh boy.
It blew up. How come it blew up?
Because the bottom is
Okay, there you go. Yeah, it didn't work, did it? Didn't work because, let me just take a little snapshot of this here real quick. Whoops. Man, I'm a little out of practice with my whiteboard here. Okay, so there's what we got. Yeah, what happened here, if we look at this function, yeah, if I try to let x equal 0, I got problems. I'm going to get a 0 on the bottom. And what are the two absolute cardinal no-nos for real numbers? I can't divide by 0, or, remember the other one? Take an even root. Good. Can't take an even root, square root, fourth root, sixth root, etc. of a negative number. Those are the only two things I can't do. Okay, so that's why we have that little meltdown there. And do you suppose the function exists there? I mean, it might, but, well, actually, this one doesn't. This one I can tell you it doesn't, because we actually know what the function looks like. But maybe in some other weird function, there's some other displaced point there or something. But no, it doesn't. It can't. It's against the rules for it to exist there, right? This is not a piecewise function. That's the only behavior we have. And we absolutely cannot have 0 on the bottom. So the function does not exist there. Now, what is the limit of this function as x approaches 1? As the ant is trying to step on 1, what is the limit of the function? And now we're kind of getting at why the limit is actually the y value. And the way, I'll write this down in a second, but the way we would say this mathematically is the limit of f of x as x approaches 1, aka as the ant is about to step on 1 from either direction, is what? What y value does he anticipate standing on? 3. Aha. Okay, but it doesn't exist. And there you have a pretty good example of a numerical approach to finding a limit. Just keep choosing arbitrarily values that are arbitrarily close to 1 and increasingly close to, or whatever the number is, 1 in this case, and see what the trend is. What are the y values approaching? What's the behavior? Well, clearly the one value that seems to be stuck in the middle here is 3. Okay? Now, notice one other thing, and this is just kind of a dorky, geeky math thing, but notice that if you look at, and this is important, I think building intuition in calculus is hard to do, but it's probably the most important thing. Notice that as we pick values that are symmetrical in terms of their horizontal distance from 1, so either down to 0 or up to 2, notice that these two values are not equidistant from 3, are they? It's skewed a little bit, right? Because, and the reason being that this function is not a straight line, it's curved. Right? And so we maybe would expect that. But as we get closer, what do you notice about those differences? They get more symmetrical, don't they? By the time we get down here very, very close, they are absolutely symmetrical, at least out to that many decimal places. Explain that to me. Why is that?
Because when you zoom in, how far it is this way.
Ah, good. Because when you zoom in, things get flatter, right? That's another important concept in calculus that we'll get to. As you zoom in on something and get closer and closer, you can flatten out curvature, right? And that's a big deal. And that'll make a lot more sense in a couple weeks maybe than it does right now. But in the same way that if aliens were to beam down to around Pendleton, and they had no idea where they were, just beamed here, they didn't come in a spaceship, they just beamed down here, they might think that Earth was pretty flat. Right? If you just took a snapshot of a wheat field outside of Pendleton, man, the Earth looks pretty darn flat. Of course, we know it's not. Astronauts on the moon could reach up and blot the Earth out with their thumb. And so clearly it's pretty curved. But as you get closer and closer to a surface, it looks awfully flat. In the same way, that same thing happens with functions. Okay, so let's get on to the definition. Don't want to do that. You know what? Maybe I don't yet. Maybe I won't do that until I want to just make sure I cover this. The assignment follows very closely this book. And so I think we won't. Yeah, I'm going to. I think it's worth it. Okay, how do we say this? Mathematically speaking, how do we attach, we got this concept, how do we say this stuff mathematically? We would say, for example, that because as x approached 1, we got a value of 3, we would say that the limit, and that's how we just abbreviated it as LIM for limit. The limit of f of x as x approaches 1, that's what that means. I'll write this out too, is equal to 3. Okay? That's how we say it. Okay? Write that. That's an important word. Okay? Notice we didn't say when x is 1. It's when x approaches 1. That's it. Okay? That's the informal definition of a limit. And the way we typically write that to represent all cases is this. The limit of f of x as x approaches a equals L, where a is the x value that the calculus ant is walking towards, and L is the y value that he anticipates standing on. So in other words, the point that he thinks he's going to get to has an x value of a and a y value of L. Whether that actually exists, who knows? Doesn't matter. Okay? Now, next step is, we know what limits are, right? We've seen how we can sort of visualize them graphically and point to them on a graph. We know how we can maybe use a spreadsheet or a calculator or something to try to capture the behavior and what's the trend by plugging in numbers. Let's take a look at some limits, some kinds of functions that have places where there are no limits. Can anybody take a guess here? Can you think of a case, a function I could draw, where that behavior doesn't exist, where ants approaching from either side would not anticipate landing on the same point, or any point for that matter? Can you think of an example where ants, yes sir?
Well, like tangent graph.
Tangent, okay, tangent, you mean like what, okay, so it's got a vertical asymptote.
Yeah.
Very good, there's one case. So let's title this Places Where Limits Do Not Exist. And one is going to be a vertical asymptote. I think in the book they call it infinite behavior. What do they call it here? Unbounded behavior. Okay, which just means vertical asymptote. Okay, let's look at an example. Here's our function, and here's the vertical asymptote. Okay, somebody explain to me here. That's one of them. Why? Why does that fail to work? Yes, sir.
Sure, because you know it's an asymptote, so you don't anticipate being there, because you know it doesn't exist.
Well, yeah, because, right, okay, as the ant walks up this increasingly steep infinite peak, as he gets closer and closer, let's say that this is the value A that he's approaching. That's the x value he's approaching. As his x value approaches A, does he blindly ever anticipate standing on a point? Think about the behavior. Every step he takes forward, is taking him increasingly high, right? And so as he gets closer and closer, when he's taking steps down here, here's a good way to illustrate this. As he's taking steps down here, let's say his steps aren't microscopic at first. They're sort of large. So he goes from there to there. Well, he only increases by a tiny bit. His next step, well, he increases a little bit more. Next step, a little bit more, etc. By the time he gets up here, look at this. From there over to there, that's a pretty big jump. That trend's only going to continue, isn't it? Every step he takes forward, he's jumping up by bigger and bigger amounts. So does he ever get to settle on a point that he thinks he's going to step on? No, because his steps are actually infinitesimally small. He's always moving closer to that point A, right? And so every infinitesimally small step he takes, he's moving up by a larger and larger amount. It's a runaway train, right? There's no one point he can ever say he's going to step on. The only point, if you could pick one, he would say, I'm just going to end up infinitely high, but of course that's not the point, right? So there is no place he can ever anticipate being in this case because of this runaway behavior. It only gets higher and higher, right? That make sense? It's happening from both directions. So unbounded behavior, that's one place where a limit does not exist. The limit does not exist at A there, okay? Does it exist at a little bit less than A?
Yes.
It does, sure. A little bit less than A, that's not actually on the asymptote. And so, yeah, he's walking up a steep hill, but then he knows I'm going to step there. I think I'm going to step there anyway, right? It's only at actually A, which would be infinitely high, that he can never settle on a final location. There's one kind. What's another kind? That was good. Any other ideas? What's another one? That's actually a harder one. There's one that's pretty straightforward. Let me repeat what I said. Now remember, for a limit to exist, ants walking from either direction would have to anticipate stepping on the same point. Or one ant that's approaching it from the left and then from the right would have to agree that he's going to end up on the same point. Good thing. Okay, I heard it, yeah.
I think it's the horizontal asymptote.
Not necessarily that, but what was it? Piecewise function, yeah. What if I have something like this? So a function that has a break in it. In the terminology of the book, they call it, this is our second example, behavior that differs from left to right. I think that's actually kind of a bad way to describe it. Piecewise function's a lot more concise. So it's a break in the function. And we can see that right here. This is, and it doesn't even matter if maybe that point's actually included down here. It doesn't really matter. If that's our function, as the ant takes his little ant steps from the left, and this wouldn't have to be flat, it could be slanted for that matter. As he takes his little steps from the left, he anticipates stepping where when he gets to A? The left ant anticipates where? Yeah, he thinks he's going to step right there, right? He says that's the limit, okay? What about that same ant or a different ant approaching from the right? Where does he think he's going to step? Yeah, he thinks he's going to step right there. Because they disagree, it doesn't work. We can't agree on a single location that the ant would always think he's going to land on, right? And so therefore we would say that here's another example of a kind of function where a limit does not exist at that point. Does it exist right there? Sure. Then ants walking from either side both agree right there, right? It exists there, it exists there, it exists there, but it does not exist at the one location where there's the break. Okay? The third one is a weird one. I won't even ask you about that one because it's very bizarre. You don't see it very much, honestly. Called oscillating behavior. And I'll tell you what, let's actually show you that I'll pull up the calculator and we'll look at this one. Okay. Okay, so what if I put in, what's one that would work here? If I do sine of 1 over x, that will work. Oops, I gotta keep forgetting I can't. I gotta go. Gotta use the keys on here. Okay, there we go. Let's look at this on a window from -1 to 1. And we'll go by 0.1s, how about? And we're just going to go zoom fit, zoom 0. Holy smokes, what's that thing doing? Look at that. It's crazy. What's it doing? Let's make the window. That's weird, huh? Look, it's going. If I zoom out, it looks fine. If I make the window bigger, let's go zoom 6 real quick. So I'll change the x values from -10 to 10, and then I'll turn around and go zoom 0, so it fits it vertically, and it looks fine out here. It looks real nice and smooth, and it's fine over there. But when we get to that middle, it's crazy. Let's make the window go from, instead of going from -1 to 1, let's make it go from -0.1 to 1. How about -0.1 to +0.1? Sorry. And we'll go zoom 0. You know what zoom 0 does, right? Zoom fit. It takes the x values that I've established, and it's going to fit the y values, so it stretches the window out to capture the whole function, but it doesn't cut it off. Does that make sense? Wow. Maybe it'll get better if I get even smaller. Let's try going from -0.01 to +0.01. Maybe that'll help. Let's see what happens. Let's go for 0.001 even. That's got to help, right? Getting close like that. That always helped with the other limits. It's smooth. Didn't I tell you functions smooth out when you get closer? So that's bound to work, right? Maybe I should have said some functions. Because watch this. It just gets worse. Yeah, that looks pretty smooth, doesn't it? Yeah. In fact, would you agree that the trend has been the more compressed I make the window, the worse it gets, actually? Right? Yeah. So this is what we call oscillating behavior. It's kind of counterintuitive in a way, because the more we focus in, the more frenetic the behavior of the function gets. Now, why is that? Let's look at this function real quick, and you tell me why you think that is, because this is another good kind of a topic. We could talk about this for hours if we wanted to. If we take the function f of x equals sine of 1 over x, what's going on there? And I'll give you just a little hint, to give you some vocabulary at least to discuss this. That's actually a composition of two functions, isn't it? It's a sine of something, and that something is an inverse function. It's 1 over x, right? So this is the part that we need to worry about. What do you think? Why is that getting so wacky as we get closer to 0? Yes, sir.
Well, if x keeps becoming a smaller number, and dividing by it, it's just bigger.
At an increasing rate, right? Yeah, if we were actually to graph the inverse function, let's just focus on the red graph for a second. What if we were to graph, if we graph this function, it looks like this, right? The closer we get to 0, the bigger the function gets in the positive direction on the left side, or the negative direction on the right side. I get that backwards. Whoops, didn't I? That's embarrassing. See what I did?
Yeah.
It's supposed to go like this. Like that. Whoops, sorry. Okay, so, right? So the values that this 1 over x function, this inverse function, is spitting out are just getting huge. Now think about it this way. Oh, man, these periods need to be a little longer. Okay, anyway, you actually have enough to get going on that first assignment, but tomorrow we'll pick it up and do some sample problems. Oh, I need to fix something too. Bailey brought it to my attention. I gotta fix the due date on which one? Probably both of them.
1.2.
1.2, okay, I'll push that out, yeah.
Oh, yeah.